Good afternoon and welcome back to Math 104. Today's class, we will begin by looking at Unit 4. So we are just 2 units shy of finishing the course. For this particular unit, we are looking at functions and quadratics. So we're going to start off by kind of recapping interval notation, which is something that you were introduced to in Math 098 last semester, whenever you took it last. So we should start off pretty straightforward. If by any chance you took Math 096, then you would have been exposed to domain and range as well, which is fantastic. And that'll actually help quite a bit in today's session. Keep in mind, I do have videos from 098 and 096, both covering interval notation and domain and range. So if you would like to use those to kind of get some more information background to help you kind of understand the content, please feel free, watch those, and then come back to this video, okay? All right, having said that, let's take a look at Unit 4. So we are going to start by talking about interval notation. So first off, when you want to combine two sets together, so for instance, you have two separate intervals on a number line, you're actually going to use this symbol U to represent the union of both sets. Hi, guys. So you'll use U to represent the union of both sets. Notice interval notation lists the endpoints of an interval. So for instance, notice here I've written smaller number, comma, larger number. Order definitely matters. You always want to write interval notation from smallest to largest, okay? Keep in mind, like for instance, if you said, you know, what do I need to get an A in this class? You would say, well, 90 or better, like 90 to 100, right? Something like that. You would never say 100 to 90. That's kind of backwards and it doesn't make any sense. So you want to make sure that you make this order specific. Okay, perfect. In the sense that an endpoint is not included, and for instance, on a number line, you would represent an endpoint that is not included, like for instance, let's write 8. We would represent that with an open circle. So in this particular interval that I actually drew here, that I drew out, we recognize that 8 is not included in my interval, but everything above 8 is. So for instance, if I wanted to express this in interval notation, I would say, well, my smallest value is 8 and we're approaching 8. We don't actually include it. So for instance, like 8.1 is in my interval, 8.2 is in my interval. If I want to get even more specific, I could say 8.01 is in my interval, right? But not quite 8. And then we recognize that this continues on towards positive infinity. When you move to the right, you move towards positive infinity. So the upper bound would be infinity. And we'd use parentheses around infinity or negative infinity because we cannot end infinity. There is no stopping point. Now, if the value were included, so for instance, let's draw a number line again, and this time we'll use 8, we'll use a closed circle, but we'll shade to the left just so I can show you the difference between the two. We still want to write our answer in interval notation from smallest to largest. So when we think about smallest, we think, how far left are we going? Like, what does this mean? Well, this arrow implies that we are coming from negative infinity, right? That's the smallest value. We're coming from negative infinity and we're going as high as 8. Now, again, you can't close infinity, so make sure you have your parentheses around negative infinity in this case. But notice, because I have a closed circle over 8, that means I am also including 8 in my solution. When you recognize we have a closed circle here and we're including the value, that is when you will use a bracket. A bracket is used to denote closure, inclusion, okay? We're including that value. Good. So we want to just quickly illustrate each set below on a number line, and some new things for you may be these two, for instance, but let's start with this first one. So according to my interval notation here, I have my solution set includes all of the numbers from -1 to 7. But keep in mind, we have a parentheses around -1, which implies that we are going to have an open circle. So hold on, let me grab a better pen. That one's dying. So we are going to have our set from -1 to 7. We recognize it's definitely going to be open circle on -1 because we have a parentheses here, which shows that we're approaching it, but not including it. And then we have a closed bracket around 7. So we are including all of the values between -1 and 7, including 7, hence the closed circle. Let's look at the next example. This one's quite interesting because it's definitely something we haven't really seen before. Notice my first interval, -5 comma -5. What? And brackets. Okay, what this is implying is that we are including the point -5, and that's it for that first piece. We're essentially saying -5 is in our interval and just -5, not a little over, not a little less, exactly -5. But in my interval, in my solution set, I'm also, see union, I am also including all the values from -1 to infinity. Notice here that we have a bracket around -1, so we're definitely going to have a closed circle on -1 with an arrow approaching positive infinity. Let's take a look at the third example. We have from -infinity to 3, and then we have from 6 to 12. What I may start doing initially is I will write down each of my critical values, 3, 6, and 12. So we have -infinity to 3, but notice 3 has a parentheses around it. So we are actually going to have an open circle on -3. And remember, we're shading everything to the left because we're including all the values from -infinity to a +3, but not including that 3. Union, so also we are including all the values between 6 and 12, but 6 is going to be open and 12 is going to be closed. So we are not including 6, but we are including 12 and all the values that lie between them. That's how you would draw the interval on a number line for this particular set. And then lastly, notice the fourth example, 7, 2. This is not in the correct order. So unfortunately, we cannot illustrate this on a number line. Cannot be drawn on a number line because it's backwards. It's backwards. It's written incorrectly. So we cannot draw this on a number line. Recall that your number line literally goes from smallest number to greatest number. So 7 to 2 makes no sense at all. So we cannot illustrate that. Perfect. What I'm going to do is I'm going to move a little bit slower through these just to give you an opportunity to write what you think the interval notations are for each of these sets. So I want you to just take a moment and look at each of these diagrams and write down what you believe is the interval notation for each, okay? Just take a couple seconds to write these down first, and then we'll compare our work together. So I'm just gonna pause for 60 seconds. Okay, so let's take a look at each. I really like writing interval notation after I've drawn a number line because the visual guides how I write my interval notation. Notice we want to write from smallest to largest, so we know that we're going from -2 to 5. Now, because we have an open circle on -2, we're going to use a parentheses, and then because we have a closed circle on 5, we're going to use a bracket. So that's how you would express the first, the first number line in interval notation. With our second example, notice we have an arrow to the left, which implies we are approaching -infinity as our lowest value, and our highest value is going to be 3. Now, we can never use a bracket on infinity or -infinity, so let's go ahead and use parentheses. And because we have an open circle on 3, we're also going to use parentheses. With our third number line, we know that we have our smallest value of -1, with our highest value being positive infinity. When I think of these number lines, remember left bound, right bound, lower bound, upper bound, right? Always look from left to right. We have a closed circle on -1, so let's go ahead and close that, and then we can only use parentheses around infinity. For our last number line, we have negative infinities. We're approaching negative infinity, and we are including all the values up to -6. Now, keep in mind, there are two intervals here. So we're going to use U to represent the union of both of these sets, where the second set runs from 7 to infinity. And notice we're using parentheses around each. Okay, perfect. So a couple pieces of definitions that you should be familiar with. The first one is a relation. So a relation is literally any set of ordered pairs. That's it. As long as you have a relationship between X and Y, you have a relation. That's it. You can express this as a set of ordered pairs, as line segments, as equations, even as graphs. But when we talk about something called a function, it's a special type of relation where each X coordinate is mapped to only one Y coordinate. Okay, so each X value has max one Y value. If, for instance, you had a set of ordered pairs where your X coordinate appears more than once, that's a problem. If it appears more than once, it is not a function. It'll fail the vertical line test, which we will talk about. So what I liked about this particular set of definitions for a function is it kind of talks through everything. So first off, you know, a set of ordered pairs in which an X coordinate appears only once. Cool. If you're looking at an equation in which a given X from the domain can only produce one Y value, right? You're not going to be able to produce more than one Y value. Or if you're looking at a graph, you know, there's every time you draw a vertical line, it only touches the graph at most once. So it's something to think about when you consider what is a function, right? Just keep in mind, every X coordinate can only be mapped to one Y coordinate, and it must pass the vertical line test. So in terms of domain, I want you to think input, domain, input, independent X, okay? When you think domain, you are thinking of the set of all X coordinates from the set of ordered pairs. You are thinking of all the X values for which an equation produces a real number result. You're thinking of all of the X coordinates for the points on a graph. That pertains to the domain X, okay? Our range would be the set of all Y coordinates from the set of ordered pairs. It would be the Y values that are calculated by using an equation, and it would be the set of all Y coordinates for the points on a graph. The range refers to your output, your dependent variable, which is your Y, okay? X, then Y, alphabetical order, domain, then range, input, output. Okay, hopefully that's clear. And especially when you think about it in terms of alphabetical order, you know, D comes before R, X comes before Y. Domain X, range Y. Let's turn the page. Recognizing functions. So we're going to determine if the relations described below are actual functions. So take a look at this first one. We also want to state the domain and range for each of these. Okay, so if we talk domain, let's go ahead and write this out. For our domain, we simply want to list our X values. I will tell you that your first set of values is going to be your independent variable, which is going to be your X values, which means they're being mapped to your Y values. Think input, output, right? I do want to make a comment that your domain, your input, your independent variable will always include time. You see that these are years. So 1995, 2005, and 2015, these are years. And these are the price of US stamps in those years, okay? Which we obviously recognize that these are cents, 29 cents, 32 cents, 37 cents, 49 cents. This is a reference to the US stamps. Your domain is just going to include all of your X values. So 1995, 2005, 2015. We will just list the values that represent the domain. Now your range is simply your Y values. It's kind of cool, right? You're essentially just listing what you see here. Your Y values are 29, 32, 37, 49. Perfect. We have our set of Y values. Now we have to determine, is this a function or not? What I want you to notice is that the X value, 1995, is mapped to two Y values. According to this, in 1995, the stamps were 29 cents, but also at some point they were 32 cents. So because this X value is mapped to more than one Y value, this is not a function. This simply represents a relation, not a function. That X coordinate is mapped to more than Y, and that's a problem. Let's take a look at part B. This time we have a set of ordered pairs listed for our view. Notice our X coordinates. Those represent our domain. So why don't we go ahead and list our domain first? So our domain values, all of our X values are simply -1, 1, 3, 5, and 7. Our range values are going to be our Y coordinates. So let's go ahead and list those. So we have 2, 4, 6. You're probably noticing that 2 appears more than once, 4 appears more than once, and since 6 appears one time. The number of times that the Y value repeats is not important. When you list your range or your domain, you only list each value one time. Even if they do repeat, you just list it one time. So now let's think, is this a function? Recall the definition. If an X coordinate is mapped to more than one Y coordinate, then it is not a function. But check this out. -1 is only mapped to 2, that works. 1 is only mapped to 2, okay. 3 is mapped to 4, 5 is mapped to 4, and 7 is mapped to 6. Perfect. This is a function. It is okay to have repeating Y values. What's not okay is to have an X value appear more than once, being mapped to more than one Y. That's what's not okay. So think of this one as X was being greedy. It took a 29 and a 32. No, shame on that X. But in B, there were no repeating X coordinates, so we know this is a function. And I'm going to write, there is no repeating X value. It's a great way to check. It's a great way to check. If there's no repeating X value, perfect, it's a function. Okay. Next, we want to state the domain and range of our particular graph, so of this visual. We want to take an opportunity to kind of see like what's going on in this case. So again, think about domain as your X values. So I want to strictly just look at my X coordinates. At this point, my X coordinate is -2. At this point, my X coordinate is 1. And notice that we have a solid line here with an arrow. What this is implying is that I'm including all of my X values that are 1 or more. So when we think of domain, we're actually going to list this as -2, -2. And we use brackets because we're including that particular point. And we want to also include all the values from 1 to infinity, where 1 is a closed circle and you can only use parentheses around infinity. That represents our domain. Domain X values. Now, here's the part that sometimes throws people off, unless you think about it exactly for what it is. This is asking us to find the range. Well, the range is your y values. So let's think about this logically. This point has the coordinate -2, 0. This point has the coordinate 1, 0, 2, 0, 3, 0, and everything in between, 0, 0, 0. So what we're saying here is that no matter where we are, the y coordinate is always 0, and that's it. So the range in this case is simply going to be 0, 0. That's the only value in our range, and we are definitely including it. Let's take a look at our second example. Again, domain x values. This one's interesting because as I look at this line, I recognize that it's a solid line moving downwards on the y-axis. The first thing I would say to myself is, what is the x value at any of these points? When we examine the x value at any of these points, do you see that this is, for instance, 0, 1, 0, 0, 0, -1, 0, -2, 0, -3. So every time we look at this, we recognize that, okay, wait a second, the only value of x that is on this graph is 0. So my domain would be 0, 0. That's the only value that's actually in my domain. When we describe the range, remember you must go lowest value to highest value. That's how you write your interval notation, smallest number to largest number. So what I like to say is when you look for the range, think about how low, then how high, right? So for instance, check this out. And we recognize that the smallest value, the smallest y coordinate in our range is going to be found when we approach -infinity. So our smallest value is found when we approach -infinity. As we follow this graph as high as we can go, we see that we're approaching a +1, but we're not including it. So our range runs from -infinity to +1 using parentheses, since we can't include that point. All right. As always, if you have any questions, please don't hesitate to stop me. Now, after having defined the domain and range for each of those, I want to show you what it looks like to use the vertical line test. So you essentially say to yourselves, okay, if I can draw a vertical line along this graph, and as long as it hits the graph at most only once, then I have a function. But if it hits the line or the graph more than once, then I do not have a function. Let's check this out. I've given you visuals here. So for our first one, we have this parabola. And you see how I drew a vertical line here? It's pretty light, but notice that it only hits our function once. It only hits our graph one time. And I can draw that vertical line anywhere I want, and it always just hits my graph at one point. So that implies it passes the vertical line test, and yes, it's a function. With our second graph, notice we have here, okay, perfect. If we drew a vertical line anywhere, it only hits the graph at most once, so it is also a function. Same thing with this one, it's a half circle, so regardless of where we draw that vertical line, it's only going to hit the function at most once, so it is a function. Now, check out the circle that we have here below. If I draw a vertical line through this circle, it's going to hit at two separate locations. Because that vertical line is hitting at two separate locations, this relation is not a function. Notice that x is mapped to two different y values. So that's what implies failing the vertical line test. Similarly, this is essentially y squared is equal to x, so it's a parabola on its side. And recognize that if we were to draw a vertical line through pretty much any point, except for the end, of course, if we draw a vertical line at any point, it's going to fail the vertical line test because it's hitting it in 2 locations. So it's definitely not a function. Good. Okay, example 5. We're going to determine whether the following relations graphed below are functions. So same exact idea, we're just going to think about what's happening. The cool thing with these is we can essentially draw vertical lines at a bunch of places and just see what happens. Like, does it fail, does it pass, etc. We're then going to state the domain and range for each relation, of course, in interval notation. Okay, so having said that, notice for our first set of ordered pairs, we have 0, 1, 2, 1, 4, 1, 4, 3. Right away, by looking at either the ordered pairs or the actual points themselves, do you see how this is not a function? The 4 repeats, and also if I drew a vertical line here, it hits our relation at 2 points. So it fails the vertical line test. So is it a function? No, it is not. But we can still express our domain and range in interval notation. Remember that domain pertains to x coordinates. So I'm going to think about the x coordinates for each of these points. The x coordinate here is 0. The x coordinate here is 2. And the x coordinate here and here are both 4. Notice that there is no line that connects them, so it's just these points individually, which implies that my interval notation is essentially going to be the first point, union the second point, union the third point. And remember, we're referring to each of the x coordinates. Domain is only x, range is only y. Next, let's look at the y coordinates for each of these points. So the y coordinates here, here, and here are all 1. And the y coordinate for this point is 3. So we only want to include those 2. So we have 1 and we have 3. And that is how you would express the interval notation for the range. We're just focused on those points specifically that pertain to the y coordinate. Okay. For our next example, we have something called a piecewise function. And essentially all this means is that we have the line y equals 1/2 x plus 1, and we only want to look at the values from 0 to 4, right? When x is 0 all the way to when x is 4. So here's our line. Anywhere we draw a vertical line, it's going to hit the graph at most once, which is fantastic because what that implies is that this is a function. It passes the vertical line test. We want to write the domain in interval notation. So what we want to consider is what is my smallest x coordinate and what is my largest x coordinate. So because this line is continuous, right, we notice that our smallest x coordinate is 0 and our largest x coordinate is 4. If it helps, you may want to write the ordered pairs. So for instance, this one's 0, 1, and this last one is 4, 3. It may be helpful. Sometimes it is. You may as well. So our x coordinates, our domain runs from 0 to 4. Notice that they're closed circles. So we're going to use brackets around each. Next, let's focus on our y values for our range. We want to think what's the smallest y value to what's the highest y value. So essentially what we could do is we can follow this graph as low as we can go. The lowest point here is at 0, 1, which implies the y coordinate is 1. Notice it's a closed circle. We're going to use a bracket. We're going to follow this line as high as we can go. And we see that the y coordinate at the highest point is 3. And it's a closed circle, so we use a bracket. If you can organize in your mind just the fact that domain is x coordinates and range is y coordinates, then you're going to do just fine in identifying the domain and range. Let's look at our third example. We see here that we have a circle. If I draw a vertical line pretty much anywhere, look at what happens. It hits the graph at 2 spots. It fails the vertical line test. So no, this is definitely not a function. In terms of domain, let's think again, what is the smallest x coordinate and what is the largest x coordinate? Another way to think about the domain is how far left are we going on this graph and how far right? And what I mean by that is you should be able to trace your graph and you want to go as left as you possibly can. Does everyone agree that no matter which direction we go, that the furthest left point is going to be here at the ordered pair 0, 1. So I'm just going to write 0, 1 here. When I move as far right as I can go in either direction, I'm going to be here at 4, 1. Because this is a solid line, all of these points are included in my domain and range, just the ones that I've actually highlighted, right? So essentially my domain is going to go as far left as 0 and as far right as 4. Remember, you're just looking at your x coordinates, 0 to 4. We're going to use brackets because we are including both of those points. And what I'm going to write here is for your domain, how far left, comma, how far right. That's essentially what you're thinking about when you look at the domain. How far left, how far right. Okay, that's what you're looking for. Good. So then we want to actually notice what the range is going to be for this particular image here. So I want you to recognize that we are saying how low, how high, and that may help to write down. So how low, comma, how high. That will actually really help you in terms of identifying what your range is. So if I follow this circle and I want to go to the lowest point possible, that's going to be here at the point 2, -1. If I follow this graph as high as I can go, that's going to be here at the point 2, 3. Remember that the range is only the y values. So the lowest y value, the smallest y value in our interval is going to be -1. And the highest y value in our interval is going to be 3. And of course, we use brackets because we're including both of those points. Okay, very nice. What I'd like you to do is just to take a couple seconds and look at example 6 below. So what we see in example 6 are 2 graphs, and we want to determine whether or not they represent a function. And then we want to write out the domain and range for each of these relations below, okay? So first determine, does it pass the vertical line test? Yes or no? And you could do that for both of them. Then focus on each one and look at, well, how would I write the domain? Remember, domain pertains to x values and your range pertains to y values. So I'm going to give you just a minute, try this out, see how it goes. Let's pause the video. So we had a discussion over our break that these were both definitely functions. They both pass the vertical line test. So no matter where I draw the vertical line, it only hits the graph at most once, right? Even over here, we could draw a line, 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 line. It only hits the graph at most once. So yes, they're definitely functions. Now, I think the trickiest part is identifying the domain for something like this. My advice to you all is write down your ordered pairs. So this leftmost point, this point that's just sitting by itself, the ordered pair here is going to be -2, 3. When we look at this line segment, our leftmost point is going to be 1, 2, and our rightmost point is going to be 4, 2. So the first thing we do is think domain x. My first x coordinate is -2, and it's by itself. It's by its lonesome. So we learned that we're going to write our point as the point itself. So -2, -2, because you're not going in either direction. And of course, you close the circle, or you'll close the interval because it's a closed circle. But we also have more X values than just that point. Our X values go from 1 to 4, right? Just focus on your X, 1, 4. Notice we're closed on the 1 and we're open on the 4. So we're closed on the 1, open on the 4. So that's how we would write our domain. We're just focused on the X coordinates in that particular, for this particular function. Now let's talk about the range. Your range is your Y values, but you always want to express lowest to highest. Interestingly enough, at any point on this line, our Y values are 2. Correct? Anywhere you go, your Y value is 2. But here, your Y value is 3. So it turns out we're going to express these obviously separately. So our Y values are only going to be 2 and then 3. You always want this to be in order as well. There are no other Y values in this particular function. It's just either 2 or it's 3.
Professor.
Yes, Jeff.
So for the open circle, why would the 2 not be in parentheses?
I love that question. The reason being is that it's closed everywhere else except this one particular location. So
Okay.
when you have closed values for that endpoint 2, that takes precedence. If it were, and it's not going to happen, but if it were open circles everywhere, again, it's not going to happen. But if it were that it's open circles everywhere, then it would be parentheses around that too.
Okay.
But just because it exists here, etc., that's what allows us to say we definitely are including 2 because it does exist. It is in our function, despite the fact that it's open at this particular coordinate. Great, great question. Thank you, Jeff.
Yeah, thank you.
No problem. For our second example, domain, X values, think how far left, how far right. So I oftentimes like to just kind of trace our graph, right? So here I am tracing my graph, and you're noticing I'm going from left to right and left to right, okay? So if I think about this and I say, well, how far left am I gonna go? I'm gonna say, whoa, this is an arrow. So what this implies is that I'm going to continue going left, 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 and I'm never going to stop. So when we think about that, we're growing in the X direction and we are approaching negative infinity. When I follow this graph to the right, notice I have an arrow here, which means I'm going to continue to grow, 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 grow. But as I grow, I'm moving slowly more right in the positive infinity direction. I'm going to continue growing and growing and growing. So my domain runs from negative infinity to positive infinity. It's going to continue to grow in either direction. Range is a little bit different. When you think of range, think how low, how high. So if I follow this line, or I follow this graph, excuse me, this parabola, and I say, well, how low am I going? In either case, I'm going to continue lower and lower and lower and lower and lower. And essentially, we're going to be approaching negative infinity. But we do have a peak. We do have a high value. If I follow this as high as I could possibly go, I'm here at the vertex, at the highest point, which is in this case, the coordinate 1, 3. The highest value in my range is going to be 3, because remember, our Y values belong to our range. So it goes as high as 3. Parentheses around negative infinity because you can't close that, and definitely a bracket around 3 because it's not an open circle. Okay. Hopefully so far so good. Domain, how left, how right. Range, how low, how high. Let's turn the page. For our second example, our third example, I can do this. So for our third example, again, same thing. I want you to consider, well, if I drew a vertical line, does it hit the graph more than once. Anywhere you draw this vertical line, nope, it's going to hit at most once. So yes, this is definitely a function. Next, we want to think how left, how right, and we only want to focus on our x coordinates. So let's follow this graph. This is as far left as I can go, and this is as far right as I can go. So let's go to the left and see what our x coordinate is here. At this point, I'm going to write -3, -4. That's the coordinate here at this point. So as far left as we can go is going to be the x coordinate -3. And it's going to be bracket since we are including that value. Next, I'm going to follow this graph. Now, notice what's happening. There is a dotted line here, which actually represents something called a vertical asymptote. It's a fancy way of saying that no matter what happens, this line will approach this dotted line, but it'll never cross it. Okay, so meaning it'll never actually reach this dotted line, but it'll get as close as humanly possible, and it'll get closer and closer and closer. So what we're saying is at any of these values, we're essentially approaching the x coordinate 4, but we're not going to actually include it. We're approaching it, but we're not actually going to touch that line, but we're getting as close as we possibly can. Now with our range, how low, how high? Trace the graph, go as low as you possibly can. Think about what the y coordinate is. Then trace the graph and go as high as you possibly can. And think about what that tells you about the y coordinates, what's happening here. So we'll start with as low as we can go. Notice our lowest y coordinate is -4. That's our smallest. It's a closed circle, so we're going to use a bracket to include that value. And then if I follow this graph, I'm going up and up and up and up, and I'm going to continue, and I'm never going to stop. So I'm approaching positive infinity. Excellent. Our last example, looking at using the vertical line test. Let's check this out. I'm going to draw a vertical line here. Uh-oh. It hit at 2 locations. That one vertical line hit the graph in 2 locations. So this is not a function, clearly. Next, we want to think about how far left and how far right, but just pertaining to the x coordinates. The really interesting thing about this hyperbola is the fact that there are 2 of them, right? There are 2 graphs. So let's look at just this one first. We're going to do them separately. If I focus on just this graph first, how far left implies an arrow here, and it also implies an arrow here. So what's happening is I'm growing more and more to the left, which means I'm going to continue in the negative infinity direction. So essentially, we are approaching negative infinity. Now, as I follow this, I want to go as far right as I can go. Think of like you're on this line and you're trying to speed to the right, and you're like, oh man, this is it. This is as far right as I can possibly go. The ordered pair at this point, as far right as I can possibly go, this ordered pair is a -2, 0. Which means that I can only go as far right as -2 for this particular section of the graph. And that's going to be a bracket. But we have two curves here. We have 2 parts to this hyperbola. So we're going to also include the domain for this section of the graph. So let's use the U for union. And let's do the same thing. Let's trace this. I want to think how far left, how far right. So how far left is going to be right here at this point. This is as left as I can go. The coordinate for this point is 2, 0. So we see that the furthest left we can go is 2. I can't go any more left than that on this section of the graph. So my first value is going to be 2. That's my smallest x value in the second part of my domain. And then I think, well, how far right? As I look in either direction, either above or below, I see arrows. So they're essentially growing in either direction towards positive infinity. They're going to continue growing towards infinity. Lastly, we want to identify the range. This one's kind of cool because we know range is how low, how high. Follow either side. How low? That's an arrow. How low? That's also an arrow. So no matter what happens, I'm going to continue growing smaller and smaller and smaller. And essentially what's happening is I'm approaching negative infinity. As I follow in the other direction, how high? Oh, I'm going to continue growing and growing and growing, bigger and bigger and bigger in the y coordinates. So that means I'm approaching positive infinity, and that represents my range. My range is essentially the set of all real numbers. All right. If you have any questions, please don't hesitate to ask. Okay. Let's talk about function notation. Now that we actually identified how you can recognize a function, it passes a vertical line test, or if you think about the sets of ordered pairs, X doesn't repeat itself, that kind of thing. We're able to identify what a function is. Now we want to use function notation. That essentially changes the way in which we look at equations, but I still want you to think of the fact that X represents an input, right? Where Y represents an output. When we think of function notation, I want you to kind of visualize like a machine, okay? So your function is the machine. And what you're doing is you're taking an input and you're saying, whatever this value is, I want to put it into the machine, do the math, and then it'll output the Y value. So X goes in, Y comes out, boom, you have a point on the graph. Think of that function as that machine, right? Input, output. I want you to visualize that as we do these. In our particular function, sometimes you may have multiple places, multiple terms that have that input, that X, and I don't want you to panic. Everywhere there's an X in that equation, it gets evaluated for that particular value that you're plugging in, and then you'll have an output pertaining to that input, okay? Input, output. Okay, let's check it out. So we have a new way of representing, for instance, Y is equal to 3X plus 2, and that is function notation. So what we do is we replace Y with F of X. Now this F really is, negligible. We could use a G, we could use an H, we could use a J, we could use an A, whatever you want. This is just function notation. So this is a function of X, right? F of X, and that's equal to 3X plus 2. All this is saying is that this equation is a function of X, X being our input, our independent variable. So if I think about, I want to figure out what this function is when X is 3, that means I would say, for instance, F of 3, I want to figure out what this function is when X is 3. So that means everywhere you see an X, you're going to replace it with a 3, right? Because you're inputting. So this is like our machine, right? The 3X plus 2 is in our machine, and it's doing the work. So 3 times 3 is 9, plus 2 is 11. So when we punch in, when we throw in the input 3 for our X, our output is going to be 11. So this says F of 3 is equal to 11. When X is 3, Y is 11. So what we notice here is that the point 3, 11 is on that line. That's what we have to think about in terms of what this actually is saying. All right. So F parentheses X is read as F of X. It's the same thing as writing Y. It just defines a formula for calculating Y using a given value of X. Okay, it does not mean multiplication. I've seen students think that this says F times X. No, function notation does not say that. It's simply a new way of representing that function, F of X. This is a function with respect to X, okay? So just like we did before, in order to evaluate the function, you simply plug in the value, that input, plug that into the formula, and then derive the output. So let's check this out. Determine each indicated function value. So we have that f of x is equal to the square root of x plus 19. So we just want to evaluate f of 6. If I want to evaluate f of 6, I'm saying what is the value of the function when x is 6? So wherever I see an x, I'm going to replace it with a 6. Then we have square root of 6 plus 19, which we know is the square root of 25. So I'm going to write f of 6 is equal to the square root of 25. And then, of course, we know that the square root of 25 is 5. So we see that f of 6 is equal to 5. What that implies is that the point 6 comma 5 is somewhere on this function. Okay, if I were to graph this square root function, 6 comma 5 is somewhere on that curve. Let's turn the page and continue to evaluate using function notation. Given g of t, do you see how we changed the variables here? It doesn't have to be f of x all the time. This time it's g of t. This is a function with respect to t, meaning t is our input. So we want to find g of -3. We're told that g of t is 1 over 4 minus t. So if I want to evaluate g of -3, all that means is wherever I have a t, I'm going to replace it with a -3. Notice I use parentheses around the -3 because my denominator says 4 minus t. T is -3. So we want to make sure we don't accidentally erase a sign or lose something. I like to use parentheses so that we don't lose that negative. Now all we have to do is do the math. So g of -3 is going to be 1 over and then 4 minus -3. That's 4 plus 3, which is 7. So my function is evaluated at -3 and becomes 1,7. So for instance, the point -3 comma 1,7 is somewhere on this particular function. All right. Let's check out example 8. We're told that we have the function f of x is equal to 2x squared minus 3x minus 4. We want to find f of 0, f of 1, f of 2, f of -1, and then we want to plot those points on this graph and we want to sketch it. So we want to see what this actually ends up looking like. Okay, so let's check this out. Let's start with f of 0. So f of 0, that means our input is 0 and is going to replace every x value with 0. Notice that the function is exactly the same, 2x squared minus 3x minus 4, but wherever I had an x, I replaced it with a 0. 2 times 0 squared is 0, minus 3 times 0 is 0, and then minus 4. So what this says is that f of 0 is equal to -4. If you do the math, you get -4. So our first point is going to be 0 comma -4. Let's go ahead and plot that point. 0, -4, x, then y. Here we are on our graph. Let's do it again. We're going to find f of 1. Wherever we have an x, we're going to replace it with 1, but we're going to be really careful to not lose any of the pieces from any of the terms from our equation. So we have 2 times 1 squared, that's just 2. So we have 2 minus 3 minus 4, and that's going to give us -5. So we have f of 1 is equal to -5. And again, I just punch this in, 2 minus 3 minus 4. So our next ordered pair is 1 comma -5. Let's go ahead and plot that point, 1 comma -5. Perfect. Let's go ahead and evaluate f of 2. Same thing. This is a great way to graph functions if, for instance, you're not sure what this function is supposed to look like. It's a really nice way just to make sure that you're collecting a bunch of points, which should help you with graphing. And we're going to end up doing something similar to this when we learn how to graph parabolas. It's going to be less of plotting by points, which is what we're doing, and it's going to be more of using specific equations to help us. When I punch this in, f of 2, I got that f of 2 is equal to -2. So we have 4 times 2, which is 8, minus 6 minus 4. Yes, that gives us -2. Sometimes I like double checking. So we have the point 2, -2, 2, -2 right here. And let's do one more, f of -1. Go ahead and plug -1 in our equation. And you'll want to plug this in to verify what your output is. So we have 2 times 1 minus 3 times a -1, which is +3, and then minus 4. That's going to end up giving me a +1. So when x is -1, we're going to find that y is +1. So -1, comma 1. So -1, comma 1. Perfect. Now this is probably going to be a little bit hard to see, but what this actually represents is a parabola. So essentially, I'm going to use my pencil just so that I can draw this pretty well. This is going to be a U, right? So this is going to be our U essentially, and we're going to go ahead and just kind of connect these as best we can. Okay, and let's draw arrows here. So it's essentially, we have a parabola here. It's not the prettiest, but we only have a few sets of ordered pairs. So for right now, this is where we're at in terms of sketching the function. Okay, we have our parabola. Now, one of the reasons I wanted to show you something like this is because we do have a bunch of points that belong to this particular function, but how accurate is that drawing? Is this perfect? You know, did I account for all the points that are actually on this parabola? Well, one of the things that's going to help us with that is understanding where our zeros are. It's understanding where this graph, this parabola, crosses the x-axis. That's essentially what we want to look at, like where is this happening? So what I want to do is I want to first introduce you to the square root property, which is really nice, and you've actually already seen this before, except we have to be very cognizant of the fact that when we use a square root property, we're going to have 2 values and not just 1. Okay, so we're going to take a look at this and then we'll take a 5-minute break. Okay. Check this out. So notice here that we are told that if x squared is equal to a, then it must be that x is equal to the positive or negative square root of a, where a is a real number, right? So for instance, when you have the notation x is equal to 2 plus or minus 5, and we're going to end up using this kind of idea as we complete the square, as we use the quadratic formula, we have to understand what this means. So x equals 2 plus or minus 5 literally means you have 2 solutions. You have x is equal to 2 plus 5, and you have x is equal to 2 minus 5. So this is implying that x is equal to 7 and x is equal to -3. That it's literally represented by those 2 values. That's going to be really, really helpful to know. When we use a square root property to solve an equation, we essentially want to start by putting the squared expression on one side of the equals and the constant on the other side. So you essentially want to isolate the squared expression. You then want to take the square root of both sides, but you don't want to forget the fact that you need to express your answer as positive, whatever that value is, and also minus or negative, whatever that value is. And of course, you want to solve the resulting equation. You're going to use this strategy if you ever have a quadratic equation that consists of just a squared expression and a constant. Let me show you what I mean by that. Turn the page. Do you see how we have x squared is equal to 16, a squared term and a constant? If you're going to use the square root property, check this out. Let's rewrite it. Now we're going to take the square root of both sides. When you take the square root of both sides, you're actually going to be left with, notice the square root and the square cancel each other out. You're going to be left with both a positive and a negative solution. So we want to make sure we write plus and minus, and I want to explain to you why in just a second. The square root of 16 we know is 4. So what this is telling us is that x can be either a positive 4 or a negative 4. Is that true? Let's see. If my answer is positive 4, then let's see, does 4 squared equal 16? Yes, it definitely does. If x is negative 4 and we substituted that in, does a negative 4 quantity squared equal 16? And guess what? Yes, it does. Using the square root property is a nice alternative to using solving by factoring. We could have set this equal to 0. Like for instance, let's do a quick recall. I could have said to you that, okay, well, we know that x squared is equal to 16. So let's bring the 16 over. So x squared minus 16 is equal to 0. Remember this? We did this before. And then you would say, oh, this is a difference of 2 squares. I can factor that. That becomes x plus 4 and x minus 4. And then if I solve, I find that x is equal to negative 4 and x is equal to positive 4. Well, guess what? I found those solutions like about 20 seconds faster than had I set this equal to 0, factored, and then solved. But they gave you the same result, positive and negative 4. So I guess the moral of the story is you really could use either style. The only time you can use this style here is if it's actually factorable. This was the difference of 2 squares, which meant we could factor it. But what happens if you can't? Take a look at part B. I'm going to subtract 3 and let's see what we get, because we want to isolate that x squared term. So we have x squared is equal to, well, 27 minus 3 is 24. Okay. I'm going to take the square root of both sides because I want to get x by itself. I want to solve. That leaves me with x is equal to positive or negative square root of 24. But square root of 24, we don't have a perfect square for 24. We could simplify it. We could break it down, just like we learned in our last unit. And that's actually exactly what we're going to do. We're going to take the square root of 24 and we're going to break it down. We know that square root of 24, we want to find a perfect square, right? Perfect squares are 1, 4, 9, 16, 25, 36. Those are all perfect squares. So right away we see, oh, 4 times 6 is 24, where 4 is our perfect square. So this gives us square root of 4, which is 2, and we still have the square root of 6. So what that means is that my answer for part B is going to be positive or negative 2 square roots of 6. That's my solution. Okay, let's do one more, then we'll take a 5-minute break. Part C, we have x plus 4 quantity squared plus 27 equals 0. We want to use a square root property. So it will be useful to get that x squared piece, that x plus 4 squared piece by itself. You want it to be alone. So what that implies is we are actually going to bring 27 over. So we have x plus 4 quantity squared is equal to negative 27. Okay, so we're going to go ahead and square root both sides. We want to isolate our x term. And in order to do that, we have to open up the parentheses. So since this is being squared, we use the opposite, which is the square root. What you do to one side, do to the other. Notice the square root and the square cancel each other out. And it leaves you with x plus 4 is equal to positive or negative square root of negative 27. I hope that in your mind, you're realizing that square root of negative 27 is an issue. Square root of a negative number. We just finished talking about the fact that that's imaginary. We've got to pull I out. So the first thing I'm going to do is I'm going to say to myself, all right, well, let's take the square root of negative 27 and let's rewrite this so that it's simplified. We recall that the square root of negative 1 is I, so I'm going to bring I out. And I have square root of 27, but I can simplify that more. Let's think of a perfect square that goes into 27. Well, that's got to be 9. 9 times 3 is 27. So let's rewrite this as I times the square root of 9 times 3, where 9 is our perfect square. When I rewrite this, I get 3i square roots of 3. The square root of 9 is 3. We still have an I. We still have a square root of 3. So what that means is that my answer so far is x plus 4 is equal to, remember, I left this alone. I haven't done anything with this yet, although I will, is equal to positive or negative. And then square root of negative 27 is the same as 3i square roots of 3. The only thing we have left to do is to get x by itself. To get x alone, we are going to subtract 4. When you subtract 4, please, 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 please place this in front of your plus and minus. So your answer is going to be written x is equal to negative 4 plus or minus 3i square roots of 3. And those are your solutions. Okay, let's take a 5-minute break just so you can digest all of this material, and then we'll continue with this idea. 5 minutes starting now. Okay, let's continue with this idea for part D. For part D, we have 2 times x minus 3 quantity squared minus 56. It would be reasonable to say, well, I know I have a term that's squared, so why not bring the 56 over? So we're going to start by adding 56 to both sides. So now I have 2 times x minus 3 quantity squared is equal to 56. That goes away. Okay, so far so good. But recall, we want to get the x squared term essentially by itself. Right now I have a coefficient of 2, which is a problem. So let's just divide both sides by 2 and get rid of it. So then we have quantity x minus 3 squared is equal to 56 divided by 2 is 28. So that actually worked out. It's okay if it's a fraction. That happens sometimes. Don't fear that. It's not a big deal. You'll just end up working with a fraction instead. We want to get rid of this square, so we must square root both sides. So what we see here is that x minus 3, right, the square and the square cancel each other out, is equal to positive or negative square root of 28. Let's go through the same process. Square root of 28, let's break that down. So when we think of 28, I want you to think of, okay, 4 times 7, right? Where 4 is your perfect square. I always like highlighting just to kind of, be consistent as we move through. The square root of 4 is 2, and we still have the square root of 7. So now I have here x minus 3 is equal to positive or negative 2 square roots of 7. All I have left to do is get x by itself. So in order to do that, I'm going to add 3. Add 3 to both sides. That leaves me with x is equal to 3 plus or minus 2 square roots of 7. If they were like terms, you'd actually combine them, but they're not like terms. Like for instance, if it were just 3 plus or minus 2, well, I would say 3 plus 2 is 5 and 3 minus 2 is 1. I would say my answers are 5 and 1. But because this is 3 plus 2 square roots of 7 and 3 minus 2 square roots of 7, those are your 2 answers. Okay? And they're actually not like terms, so you can't combine them. For our last problem, notice that we have 0 is equal to 9 minus x plus 5 squared. What I would do if I were you is I would notice that I can add this squared term and bring it over to the left. If I add this squared term and bring it over to the left, then it becomes positive, which is actually really nice. Remember, you can only add or subtract terms. So that leaves me with 0 plus x plus 5 squared, which is just x plus 5 squared, is equal to 9. So we have our squared term and our constant. That worked out pretty well. We were able to bring that term entirely to the left-hand side of the equation. We are going to square root both sides. That leaves me with x plus 5 is equal to plus or minus square root of 9. Well, we know what square root of 9 is. Square root of 9 is 3. So we are left with x plus 5 is equal to plus or minus 3, since square root of 9 is 3. So let's go ahead and rewrite this just so I can see what's happening. X plus 5 is equal to plus or minus 3. Now I'm going to subtract 5 to get x by itself. And that leaves me with negative 5 plus or minus 3. We can actually do this math, which is pretty cool. We can actually evaluate these solutions. So we have that x is equal to negative 5 plus 3 and negative 5 minus 3. So let's actually do the math. Let's simplify these. Negative 5 plus 3 is negative 2. And negative 5 minus 3 is negative 8. And those are your 2 solutions for part E. Do you have any questions on this whole process? Is anything unclear that I can kind of help and clarify?
This is going pretty good so far.
Awesome. Okay, very cool. All right, let's turn the page. Remember when we talked about perfect square trinomials way back in Unit 1?
Professor?
Yes.
I didn't mean to interrupt you. Can I have like 5 more seconds with that last page?
Yes, absolutely. Absolutely.
Just about.
And what I'll do as you're looking through this is I'll just kind of recap the general gist of this. So when you want to use a square root property, think about the fact that you need a term that's squared, and then you need a constant, right? A constant meaning it doesn't have a variable with it. This whole square root property piece won't work if, for instance, you have something like x squared plus x equals 5, right? Because you have a squared variable and then a linear term with the variable, and you don't want that. It has to be a squared term and a constant, squared term and a constant. That's how you know.
Thank you.
You're very welcome. So, okay, we recall from Unit 1 the idea of perfect square trinomials, right? Take a look at this. X squared is a perfect square because x times x is x squared. 36 is a perfect square because 6 times 6 is 36. We recall that we can actually write the factored form as x plus 6 times x plus 6. Your signs are the same, they're both positive. Let's double check. X squared, 6x plus 6x is 12x plus 36. But we also learned that's the same thing as writing it as x plus 6 squared. Do you kind of see where we're getting? Like, do you kind of see where we're heading to? Like what it is that we're trying to do here? Starting to look like what we were just playing around with. Look at part B. Let's factor this one. Notice this is definitely a perfect square trinomial. 9x squared, that breaks down into 3x times 3x. 25 is a perfect square, that breaks down into 5 times 5. Your signs are the same. They're both going to be negative. So when we factor this, we say, well, I know that 3x times 3x gives me 9x squared. I know that 5 times 5 gives me 25. And I also know the signs have to be the same, and they're both going to be negative. If you distribute, you'll get the negative 15x and negative 15x, which gives you negative 30. So you know that you did this correct. So essentially, we would write that as 3x minus 5 squared, right? Like that's not an issue. We know how to factor, we know how to rewrite it. Okay. Now, in terms of squaring a binomial, we've done this a million times, so I'm just going to show you part A. X plus 3 squared is the same as x plus 3 times x plus 3. You end up writing it twice. It's not enough to just square each piece, which is what reminds us of this idea of perfect square trinomial. When we distribute, we get x squared plus 3x, which is plus 6x, and then plus 9. So we get a perfect square trinomial, but we knew that. And I'm not going to worry about B at this point, because it's the same process. So what I want you to notice is the following. When you're looking at your perfect squared trinomial, and when you look at the factored form, right? We could do that here. Look at your perfect squared trinomial. Look at your factored form. Do you notice that, for instance, this 9 is the square of your term inside the parentheses? Or that this 36 is the square of this term in the parentheses? Same thing, this 25 is the square of this term in the parentheses at negative 5. That's an interesting feature to note. And then I also want you to notice that isn't 6 double what's inside the parentheses? Isn't 6 here, notice here, we're going backwards. Isn't 12 double what's inside the parentheses here, 6? We're kind of starting to make connections here that I think are going to be really, really helpful. The first thing is to notice that with this positive 3, same thing with this positive 6, that essentially that 9 is the square of that positive 3, right? And that this 6 is double that 3. So just something to think about for a moment. In general, the relationship between the constants and the coefficients in a perfect square trinomial and its equivalent binomial are the following. If you ever wanted to just take a perfect square trinomial and instantly write it as the square of a binomial, all you have to do is consider whatever your B term is, you simply cut it in half. That's what would go inside the set of parentheses. You cut it in half. So for instance, if it were 12, which was our original, let me just move this up for a moment. Our original, our B term was 12. So inside it'd be half of that, which is 6. Our B term is 6 and half of that is 3, right? So something to consider. In each case, our leading term is 1x squared, right? And this one, when we break it up, it's 1x squared. So that's very different from part B. We're just focused on when our leading term is a 1x squared. So that term inside is going to be half of our B. Another thing to consider is in a perfect square trinomial, this last term is always going to be our term inside squared. So essentially, it is going to be h squared in this case. It's really, really important to make the connection between the two. What I'm going to do for a moment is I'm going to write out our perfect square trinomial from part A in example 10, and I'm going to write its factored form as the square of a binomial. Notice that 36, and notice that 6 is half of 12. So that's how we get that 6. I'm going to write the other one as well, x squared plus 6x plus 9. We know that this is x plus 3 squared because half of 6 is 3. And we also know that 3 squared is 9. So it like checks out. These are exactly identical to each other. We can verify that. It's really important to be able to go back and forth. Okay, let's turn the page. We are now ready to solve a quadratic equation by completing the square. Okay. Our goal is to add a constant on both sides of the equation sign so that we can write that left-hand side as x plus a number squared. We want to be able to rewrite that so that we can write x plus whatever that number is squared. Then we're going to use the square root property to solve. Okay, so we have to rewrite it so it has that squared piece and a constant, just like we saw with all of our previous examples. It was a squared piece and a constant. It was a squared piece and a constant, right? We're looking for that. So sometimes we have to manipulate the equation in order to make that happen. Okay, so are you ready for this? What I would actually recommend is please just put your pens and pencils down. I just want you to actually observe. That's all I want you to do. So just take this in for a moment, and then I'll pause the video and give you an opportunity to write this down. Okay. The first thing I'm going to do, notice it says complete the square. So this is really important. The first thing I'm going to do is I'm actually going to write this out and leave a gap here. I'm doing this intentionally. I want to complete the square. What we learned about is the fact that if I wanted to complete this square, I essentially want to write this where it's the square of a binomial, right? Where this term is going to be half of my b term. So that means it's going to be half of my -8, which is -4. And that my third term here in my perfect square trinomial is the square of this value. So the square of -4 is positive 16. But you're probably thinking, you're not allowed to just add 16. And my response to that is, I can if I add it to both sides of the equation. So what I did was I manipulated my left-hand side of the equation so that I can complete the square. You do that by taking half of the b term. So you take it by you do that by taking half of the b term, and then whatever that value is, you square it. And whatever you add to one side, you add to the other. Now, -4 times -4 is a positive 16, which is why I added 16 to both sides. Okay, so it may help to write that you took half of our b term and you squared it. What you do to one side, you do to the other, which means it's now equal to, well, -20 plus 16 is a -4. Go ahead and take a moment to write all of that down, and then we'll solve this together. So now that we have, and I'm going to rewrite it because it's a little messy, x minus 4 squared is equal to -4, I can use the square root property. I'm going to make a note. Now we can use the square root property, which means I can take the square root of both sides. So let's check this out. Square root here, square root here. That's going to give me x minus 4. That's going to be positive or negative square root of -4. If we do a little bit of side work, that square root of -4, because it's a square root of a negative number, we always pull that I out. So we'll take I square roots of 4, and we know that square root of 4 is 2. We would write this as 2i. So when I go back and replace, I have x minus 4 is equal to positive or negative 2i. Now I just got to get x by itself. In order to solve for x, I'm simply going to add 4 to both sides. And voila, I have my answer. X is equal to 4 plus or minus 2i. Remember that that means that x is equal to 4 plus 2i and x is equal to 4 minus 2i. That's what that means, okay? So those are your solutions. 4 plus 2i, 4 minus 2i. That's how you would write out your answers. There are 2 of them. The other thing I want you to note with this particular example is that my leading coefficient is 1. It's a 1x squared. It's not in any other number x squared. It's always a 1x squared. That's actually something we want to be really careful of when we complete the square. We always want our leading coefficient to be a 1. So as long as you're ready, let's check out part B. For part B, we have 3x squared plus 36x minus 33 is equal to 0. I don't know about you, but do you see that that 3 is jumping out at you? It's like slapping everybody in the face, right? It's like, I'm here. Let's divide out 3 from every term. Let's divide out 3 first. So we're going to divide every term by 3 so that we can essentially make sure that our leading coefficient is a 1. So that leaves us with x squared plus 36 divided by 3 is 12. 33 divided by 3 is 11. And of course, 0 divided by 3 is 0. Okay. If we are going to solve this by completing the square, we need to first move the constant term over. Okay. You move the constant term over so that we can look at these 2 terms and focus on completing the square. So let's bring the 11 over. So I have x squared plus 12x. I'm going to leave a gap, just like I did before, and that's equal to 11. Now I want to complete the square. I want to write this as the square of a binomial, right? That's my goal. So in order to do that, I want to take half of this 12, which is 6. So half of 12 is 6, and it's a positive 6. And then I want to double this 6, right? So we want to square it. So 6 times 6 is 36. And what you do to one side, you do to the other. So I squared the 6 to get a 36. So I'm completing the square. And if I add it to the left, I have to add it to the right. Otherwise, I'm totally changing this equation. So half of your B term, square it, and that's what you'll add to both sides. Awesome. Now that I have x plus 6 squared is equal to 11, I can solve this. I can use the square root property. Using the square root property, I take the square root of both sides. Square root and square cancel each other out, so it leaves me with x plus 6. And of course, that leaves me with a positive or negative square root of 11. Square root of 11 cannot be simplified. It can't be broken down. So we actually leave it. We don't even touch that. The only thing we're left with is getting x by itself. So we isolate the term.
Professor,
Yes.
shouldn't it be
Oh my God.
47? Sorry.
Thank you so much. So here's what happens when you completely neglect what you did here. So don't make the mistake that I just made. 11 plus 36 is not 11. 11 plus 36 is definitely 47. See, I was just making sure you're paying attention. That's all. That's what happened. That's what happened. Let's fix this. Pretend it never happened. You know, I appreciate when that happens because stuff like that happens all the time when we're working on homework, you know, at home and kind of going through the process. Stuff like this happens all the time.
I think when I was learning this before, that was my number one mistake this entire, like every time I did it, was forgetting to add that one.
So that's why. Okay, so this is a perfect illustration then. Like, be careful. Be careful. If I could make the mistake, anyone could make the mistake. Okay, so be super careful. 11 and 36, 47. You take the square root of both sides. So we have positive or negative square root of 47. With 47, there are no perfect squares that go into 47, which is fine. Again, it's not a big deal, but we do still have to solve for x. We still want to get that by itself. So I'm going to subtract 6 from both sides. And that leaves me with x is equal to negative 6 plus or minus square root of 47. And that represents our final answer. Okay. Good. I love this because you're able to use this technique literally anytime you want to solve a quadratic equation. Completing the square is one of your 3 strategies that you'll use to solve a quadratic equation. What it means by solving is figuring out what the x-intercepts are, figuring out what those zeros happen to be. Using the quadratic formula or completing the square are 2 methods that will always work. We know from experience factoring doesn't always work because we can't always factor every single quadratic. So what I would stress to you all is that it's super important to be incredibly familiar with both completing the square and the quadratic formula. I will say I want to add the square root property to that because you can solve quadratics, but not every quadratic equation can be solved using the square root property either. Okay, so you want to be careful. Factoring the square root property, they have limitations, of course. And then if you have completing the square and quadratic formula, those will always work. So just keep that in mind, which means completing the square, you really want to like hold on tight to that and say, I need to master this technique. Let's turn the page. What I've done here is I've essentially broken down how you solve a quadratic equation by completing the square, but that's essentially what we just did. So let's try this again. And actually, why don't you two kind of throw out some ideas and we'll work through this together. That way, those of you who are watching this video at a later point, you can kind of hear the dialogue that comes into play. So we want to solve the equation by completing the square. So let's take a look. We have negative 2m squared plus 4m plus 16 is equal to 2. Or I can't even talk, is equal to 0. What's the first thing that's kind of jumping out at you? Like when we think about what we just did on the last page, what's something we could consider? What do you think, Jeff?
I say that the 2 can go in. You can take 2 away from everything. You can divide the 2 out from everything. The other thing I want to point out is that my leading term is negative. So because my leading term is negative, not only do I want to divide every term by 2, but I actually want to divide by negative 2. I want to get rid of this. I want my leading coefficient to be a 1. What I do want to point out is step number 1 here that says, remove the x squared coefficient if it's not 1. And you do that by dividing every term by that coefficient. So check this out. We're going to divide every term by negative 2. Every single term. We want our leading coefficient to be a positive 1. That leaves us with m squared minus 2m minus 8 is equal to 0, because 0 divided by negative 2 is 0. Okay. The next thing we learned, which was our second step, was we wanted to bring the constant over to the other side. We wanted our m squared minus 2m, our square term and our linear term by themselves. And we wanted to bring that constant over because we want this to be a gap. Remember that? We leave this like a gap. So let's bring the 8 over. That gives us m squared minus 2m with a gap is equal to 8. I like leaving that gap there because it's a hint. Oh, I know what I got to do next. I got to complete the square. So when we think of the process of completing the square, let's write out the parentheses with the square on it. Let's keep the 8 there. We know our leading term is m.
So we want to take half of our b term, right? So we want to take half of -2, which is -1. And then we want to square our -1. So we want to square it. -1 times -1 is +1. What you do to one side, do to the other. If you're going to add a 1 on the left, you've got to add a 1 on the right. That way your equation stays completely balanced. So then that means this becomes a +1. And we're going to clear that up. That simply becomes a 9. So we have n-1 squared is equal to 9. So far, that's great. I'm liking what I'm seeing. But now we have to use the square root property to finish this problem. So let me rewrite this up here so that it has a lot more room. n-1 squared is equal to 9. Now let's take the square root of both sides. The square root and the square cancel each other out. n-1 is equal to positive or negative square root of 9. That's huge. You don't want to forget that plus or minus. We know that square root of 9 is 3. So we have n-1 is equal to plus or minus 3. And now I want to solve for m by adding 1. So let's add 1.
Sorry.
Yeah, go for it. And then we have 1 plus or minus 3. We need to evaluate each piece. We have 1 plus 3 and we have 1 minus 3. So 1 plus 3 is 4. 1 minus 3 is -2. I'm going to write here we have 1 plus 3 and we have 1 minus 3. We don't want to forget that we have those two solutions. And those are my answers, a +4 and a -2.
This is a lot, Doc.
It is. It definitely is. What I would highly advise is as you're doing these, just follow your steps piece by piece. 1, make sure your leading coefficient's 1. Then bring your constant term over. Take your b term, cut it in half and square it. Add that to both sides. Do this whole thing of like half square. Obviously combine those two together. Then just use the square root property and then solve. I know I'm saying like just, but you're right. It is a lot. I'm just hopeful that it has a flow that makes sense. Like, okay, now you have to do this. Okay, now I have to. You know, I want it to feel like, okay, I know what my next step is because it's the only next logical step. I know it's 150, but I would like to do just one more, because I want to show you what happens if B is not like a nice number, okay? Because I don't want you to panic. So looking at part B, what's the very first thing we have to do? According to our steps for using completing the square, what's the first thing I have to do? What do you think?
Maybe find, as you did in the previous question, maybe find some kind of GCF and under and kind of put them under each of those.
You're right, and divide it out. Here's the uncomfortable part. It doesn't have to be a GCF. This is the uncomfortable part. If you needed to, you could just divide by whatever that coefficient is. That's why it's so uncomfortable. Check this out. I need my leading coefficient to be a 1. So whether I like it or not, I'm going to divide by a 4. It's going to be uncomfortable because check this out. So we get x squared. Yay, that was our goal. Cool. Then 20 divided by 4, well, that's 5. That's no big deal, right? But then, holy crap, we have 35/4. I can't simplify that. But we're going to have to be okay with working with fractions. That's why I wanted to do this last problem before I left you today. So 35/4, and that's going to be equal to 0. So we divide every term by my leading coefficient so that it becomes a 1x squared. I always take my constant term, step 2, and I bring it over. I'm going to take this constant term and bring it over here. The only way to do that is by subtracting it, right? Because it's a plus 35/4. So that gives me x squared plus 5x, leave a gap, is equal to negative 35/4. Remember, we subtracted it from both sides. If you want, I can squeeze that in there. So minus 35/4 minus 35/4. So I subtracted that from both sides. I'm gonna leave a gap here. Chanel, stick with me, but I'll be right with you, okay? So we need to complete the square. Here's another place where this is gonna be really uncomfortable. We know that my leading term has to be an x. We still know that in order to get this term here, we have to take half of our b term. Half of 5? Well, that's not even because 2 doesn't go into 5 evenly. That's okay. Half of 5 is 5/2. Isn't that half of 5? We still have to square it. We still have to square 5/2. 5/2 times 5/2 is 25/4. 5/2 squared is 25/4. What you do to one side, do to the other. Add that 25/4. So I'm going to highlight that on both sides. Okay, so let's do the math. Negative 35/4 plus 25/4. When you think about this, you're just combining the numerators. Negative 35 plus 25 is a negative 10. So we have negative 10/4, which by the way reduces, and you should reduce. So now I'm going to rewrite this. We have x plus 5/2 squared is equal to, let's reduce this, divide both by 2. So that's negative 5/2, because I just divided each by 2. Now, the only logical next step that we have is to take the square root property, right? Is to use the square root property. Square root both sides. Boom, boom. That leaves us with x plus 5/2 is equal to positive or negative square root of negative 5/2. What we'll want to do with that square root of negative 5/2 is we actually want to bring out that negative by bringing out that I, okay? And we also have to clean this up. So give me a moment. You're about to be like, oh my God, are you freaking for real? So let's take that square root of negative 5/2. We're going to bring out the I. So far, so good. That's all I did. There's a problem with this. We have a radical in the denominator. So I have I square root of 5 over square root of 2, which means I now have to rationalize. Oh my God, I can only feel the fact that you're like, this is just a lot. This is way, way, way more than I expected. Rationalize by multiplying by square root of 2 over square root of 2. Okay, that's going to give us I square root of 10 all over 2. We just had to rationalize here. And I'm going to write here that we rationalized, because we can't have a square root in the denominator. So now we have x plus 5/2 is equal to positive or negative I square root of 10 over 2. And now I'm going to bring the 5/2 over and write my solution. X is equal to negative 5/2 plus or minus I square root of 10 over 2. And there's your solution. Woo-wee! Yes, there were so many different moving parts to this, but really it's an opportunity for you to put all of the things that you have learned together in one problem. All the steps for completing the square combined to one problem. Do you have any last minute questions before I let you go today? Okay, hearing none. Thank you so much for joining me. That was super, super awesome. I will be filming tomorrow. I'm going to do that through Zoom again so that I can pause the recording as I go. So if you'd like to join me, I believe I said it was going to be at 9:30 tomorrow. So if you have time, cool. If not, I know, James, you work over the weekend, so I understand if you can't make it. But other than that, enjoy the rest of your day. See you guys.
See you later, Professor. Thank you.
You're welcome.